Hi and welcome to video 12 in this video series on Newton's laws and forces that comes from Unit 4, Topic 2, the Specialist Math Curriculum. So today we're going to talk about the third type of force. We've talked about frictional forces and the normal reactive force or normal reaction force, and you'll see those here. Today we're going to talk about forces on an inclined plane. So there's our normal reaction force, there's our frictional force, here's a force that's pulling an object along a plane. And this is weight due to gravity, which is equal to m, the mass of the object, times g, the gravity that we have. Typically, we're dealing with something on Earth, but wherever we are. And this turns into this force diagram. But today we're going to talk about this inclined plane and the inclined plane diagram. Now, in this particular case, we have a reactive force, again, that is normal to the plane. So that comes out from the plane at a right angle. But weight is directed straight down. So they're not actually in a straight line anymore, and we have to be cautious and aware of that. We have a frictional force which opposes the force that's trying to move or moving the object. Now, so in this case, we have a pushing or pulling force on the object. We may have a situation where, in fact, the object hasn't got this force. That force may not exist. So instead, weight, which has got a small component heading down the plane, there's nothing else heading up the plane, is heading this way. That is a component of weight. That's the I component of weight. And that means that the frictional force will actually be holding the block on the plane. So if you imagine you put a box on a sloped driveway, for example, the only force that's actually been applied inadvertently to that box that's not pushing it into the ground or out of the ground is a little bit of that weight or gravity pulling it down the slope. And if it's a steep slope, there's more, and if it's a shallow slope, there's less. If it doesn't move, that's because there's a frictional force holding it in place. So this diagram could change depending on whether we've got a pulling or pushing force up the slope or whether we don't. But here's our typical diagram. Our frictional force and our normal force here. Weight, if we set our I and J to be along the slope of the plane, the weight is the only thing that we have to break into components. And we have a J component of W cos theta and an I component of W sine theta. And theta is the incline in the plane. So it turns out that if I just drop this little bit here and across there and we say this is theta, well then we get this value, which is 90 minus theta, and that gives us theta there. So it actually turns out that theta translates straight across to being inside that triangle with weight. And so we use it. It's nice. So then we get component form here. And our component form is our overall actual force, FA, I've called it in this case, and that's equal to the force being pushed up the plane in the I, positive I direction, minus the frictional force, and then minus the component of force heading down the plane from the weight, W sine theta. And because it will be heading down the plane, it makes sense that something's going to slide down a hill, not slide up due to gravity. And on the J component, and this should match out because it shouldn't be sinking into the ground, our normal reactive force is now equal to W cos theta, which is our component in the J direction. And there are our components, I and J. So let's have a look at a couple of examples. The first one is an example following on from our previous video, where we look at the same question again as the previous video, but this time the plane is on a 20-degree incline. So we have a 20-degree inclined plane, it looks like this, and that's 20 degrees. And then we have a box sitting on that plane. There is a normal reactive force. It's being pulled along the plane, so we've got to assume here that it's been pulled up the plane. I'll make that assumption. So we get our force there. We don't know much about the force. It's equal to MA. We know M, but we don't know A. This is our reactive force, and it happens to be equal to the weight cos theta. And then we have our weight here equal to mg. And so then we can split that up into its components there. And we also have our frictional force. And so in component form, the overall resultant force is equal to F, our force up the plane, minus our frictional force, that's wrong, minus W sine theta, as we got before, and there's our diagram that represents that because that's 20 there. I plus R minus W cos theta. Now, there's a few things that we know. We know, or that's J, that R minus W cos theta has to equal 0 because it's not going into the ground, it's not sinking into the plane. So this will pretty much always be the case. So R is equal to W cos theta, which means that R is equal to 20, that's our M, times G. I'll leave it in terms of G, cos of 20, that's our angle. Now, I'm going to leave it as cos of 20. That's an irrational number, and I don't want to deal with that just yet. So that's the first component. Our second thing we know is that our resultant force, which is FAI, is equal to F, which is 20A, minus FR, which is the frictional force, which is mu times R, minus W sine theta, which is 20G sine 20. Now remember, we know this entire number, and we know this entire number. We've got to work out A, but we know this entire number, and we also know mu, and we now know R as well. So we can work out the overall resultant force. So this is equal to 20 times, now A is equal to 1.875. So you might recall it's meters per second squared. In a previous video, we talked about the fact that A is equal to the change in velocity over the change in time. In this case, the initial velocity is 0. It goes from 0 to 15. A change in velocity of 15. Time is 8 seconds. Hence, A is 15 over 8, or 1.875. And so, FA is equal to MA of motion. It's the overall, which is 20 times the A of motion, which we've determined here. So this goes 1.875 here. That's equal to 20 times A, which is the acceleration applied. That's the force there that's being applied to make this motion happen. Minus mu R, and that's 0.35 times by R, which is 20G cos 20, minus 20G sine 20. And now I can rearrange this, and I get, and you can do this quietly and slowly if you want to, but I get 20 times 1.875 plus 0.35 times 20G cos 20 plus 20G sine 20. So this has to be overcoming friction. It has to be enough to have friction and that gravity-based force, and also provide the overall force. And then divide that by 20, and that comes out with an answer of 8.45 meters per second squared. But be careful, find the magnitude of the constant force. So it did actually ask us for the magnitude of the force. So I don't really have to worry about dividing by the 20. So I might just make a little change here. Imagine that was there, that was actually 20 here. And 20A is the force. The force is equal to 168.9988 newtons, or about 169 newtons. And that's a good answer because in our previous question of flat plane, remember a flat plane is going to be easier to drag a box along. We only needed to apply 104 newtons to make that drag happen. So let's have a look at example 4. In example 4, a book of mass 2 kilograms gets to a point of slipping. So a point of slipping means that the frictional force and the force being applied is actually equal. And we need to determine mu to make that happen. So we know the point of slipping happens at 42 degrees. So let's have a look. Here's our inclined plane, and here's our book. So our book's there, and on this book we have only two forces being applied. Weight, which equals mg, and our reactive force R. And we'll define our components here. Now, of course, there is a third force being applied because the weight is trying to pull the book down a table. But we're at the point of slipping. So that means there's a frictional force holding the book on the table so it doesn't quite slip. But there is nothing else applying a force. It's only that gravity that's applying a force, and everything else is coming from that. Let's now build a component-based understanding of this situation. So the overall force, which I call FA, is equal to the I components first of all. And the I components of this force are FR in a positive direction, minus our weight in the positive direction, which is, this is our 42-degree angle here. So our weight is that sine value, mg sine theta I, plus our second components, which are the resultant force in the positive minus the weight in the negative, which is mg cos theta j. And this is at the point of slipping, but it's not moving. So therefore we've got Fr max, the maximum possible friction, and we've got components equal to 0. So we get equation number 1, the resultant force is equal to, well, actually let's write it out in full. Resultant force minus mg, which is 2g cos 42 equals 0. And therefore the normal reactive force, not resultant force, sorry, the normal reaction force is equal to 2g cos 42. And our second equation is that the frictional force, Fr, and this is now Fr max because we're at the point of slipping, minus mg sine theta, which is 2g sine 42, also equals 0, which means that Fr max equals 2g sine 42. But Fr max is equal to mu times r. And that means that mu times by 2g cos 42 is equal to 2g sine 42, which just strangely changed into a 22 there. And now our mu is equal to 2g over 2g sine 42 over 2g cos 42. The 2g's cancel out, and sine over cos is tan, so mu is actually tan 42, and the value of tan 42 is approximately 0.9, but I'll write that down with a bit more detail, so it's equal to 0.900200402 ... So we say approximately 0.9. There's no units for mu, it's just a coefficient of friction for that surface, or the two surfaces combined. But that's really interesting that we get this result here as well, and we can prove it if we want to. Mu is equal to tan theta, and that's our coefficient of friction at friction max. It's equal to tan theta, where theta is the angle that you have to have it inclined for the first slipping to happen. So that's a really interesting result that you should definitely be using or considering as you move forward. So there we have it. We've talked about inclined planes, and that's video 12. All the best.